Hello, my name's Dan, and I'm one of the peer mentors here at the LRC. And I'm making this video just to go over a few retrosynthesis practice problems and just showcase how I like to solve these problems myself. In Organic Chemistry 2, there are quite a bit of reactions that you need to know, and it might be overwhelming in the beginning when trying to solve these problems and just not knowing which reactions you need to use. And what I like to do is to have a sheet of paper with all of the reactions I've learned so far, and just using that as a reference to help guide me through all these practice problems. Eventually, it is important to stop relying on that sheet of paper and just knowing which react or what reactions lead to what. But especially in the early stages, it can be a very useful resource to help you through all these retrosynthesis and synthesis problems. For our first problem, we have a retrosynthetic analysis on a carbon-oxygen bond. And when we're dealing with retrosynthesis, we are breaking a bond in order to make what's called a synthon. So in this case, we are breaking this bond specifically. So our first decision must be where exactly do we put the electrons that come from that broken bond? In this problem, we can either put the electrons on the oxygen atom or onto the carbon atom. And typically, we want to have the electrons be as low energy as possible. So knowing that oxygen is the more electronegative atom, uh, we do want to put the electrons onto the oxygen atom instead of the carbon atom. So um, here are the synthons that come from this specific disconnection. Now, it's important to understand that synthons are not the quote-unquote real molecules that are used for synthesis. Synthons are just a way for us to imagine simpler molecules that make up the product. Or another way of saying this is that you can't bottle up these two molecules in order to synthesize this product. So instead, we need to make what's called a synthetic equivalent. And synthetic equivalents are molecules that are functionally the same as synthons, but can actually be used in real life to make the product in a synthesis reaction. So we can actually bottle up these molecules and actually make that product in the problem. So this is where having that reaction sheet is very useful, as it can help guide you through or guide you to the correct synthetic equivalent. For these specific synthons, we can see that the positively charged carbon has an allylic position, which means it is adjacent to another carbon that is also double bonded to another carbon. From our understanding of reactions, we know that allylic carbons are really good for substitution reactions, and specifically SN2 reactions. So we can put a bromine on the carbon, and because this is an SN2 reaction, we can also put a sodium cation to the oxygen. And here are the resulting synthetic equivalents. For our second problem, we have a retrosynthetic analysis of or between a carbon-carbon bond instead of a carbon-oxygen bond. This makes the disconnection a bit more difficult because there isn't a difference between electronegativities. So how do we determine which carbon gets electrons? The way that the way that we determine that is through finding out what hybridization each carbon has, And from that hybridization, we will know which carbon will lower the energy of the electrons more. So the triple bonded carbon is sp hybridized, and the other carbon is sp3 hybridized. If we put the electrons onto the sp3 hybridized carbon, that will actually increase the energy of the electrons, and we don't want that happening. So we put the electrons onto the sp hybridized carbon, and that will generate our synthons. One thing to note is that this triple bonded sp carbon with the anion is called an acetylide anion, and you will definitely be seeing and using these in many retrosynthesis and synthesis problems. Now that we have our synthons, we can start making our synthetic equivalents that we will use to synthesize the product. Again, this is a perfect time to have that reaction sheet ready, just as a reference if you need it to help you through make the synthetic equivalents. So looking at the acetylide anion, we know from acetylide reactions, which are basically just SN2 reactions, that we can put a sodium cation onto the acetylide anion, and that makes the synthetic equivalent for this molecule. Now for our second molecule, this molecule is actually resonance stabilized, which may or may not be evident, but if we put the electrons from the negatively charged oxygen to the positively charged carbon, that actually makes our synthetic equivalent for this molecule, which is an epoxide. So that is it for the example problems. Just to wrap up, these are just a general guideline on how to solve retrosynthesis problems. So first, determine where to put the resulting electrons from the broken bond that will also yield the lowest possible energies. And second, creating a synthetic equivalent that is equivalent to the synthons made and can be used in a synthesis reaction that yields the original product. So yeah, retrosynthesis can be a bit difficult when starting off, but again, I highly suggest having a reaction sheet ready. And even if you don't need it, like just having that near you can help you through if you get stuck somewhere, and it'll also help you learn the reactions faster so that you don't have to waste time just staring at your screen not knowing what reaction to do. And eventually you won't even need the reaction sheet anymore because you've done so many problems that it's just become second nature to know what happens in a specific reaction. So yeah, hopefully this was helpful. If you have any more questions, don't be afraid to leave a comment into the Slack channel. And yeah,